today's class is one of the most important topics that you will be studying in this course. It is Markov Decision Processes. Okay, Markov Decision Process is the foundation stone of reinforcement learning itself. So what we will be learning in this in today's lecture is to understand what MDP is. Okay, Markov Decision Process is abbreviated as MDP, and I'll be using that very often now. And how it is related to the foundation of RL. We'll study that, okay? And then you will be going through the components of MDP itself. There are different components of MDP, different elements of MDP, when put together form the MDP itself, okay? So Markov, right? There's Markov decision process, so there's something called Markov property as well. So every RL problem should satisfy Markov property, okay? We'll study about what Markov property is, how it will be fulfilled, and why it should be fulfilled in every RL case. With that, we will see to develop a simple MDP problem, basically formulation of an RL problem, right? As an MDP, and visualize how these MDPs work in the RL setup. Okay. First, why do we need to formalize this agent environment loop? Why do we need to do that? Because we need some kind of mathematical structure here to solve the problem that we are trying to achieve here, right? What are we trying to do here? Through the agent environment interaction, we are trying to solve a problem, a task which requires a set or series of actions, right? So we need some kind of mathematical formulation for that. And Markov decision processes provide us with a very good framework of solving these, or rather presenting these RL problems as mathematical formulations. Okay? So the main components of an MDP agent, or rather MDP, is states, actions, rewards, transition probabilities. Okay? Or the transition to the next state. Right? Clear? States, actions, rewards, and the transition probability. Okay? Here, please, if you do not understand anything, even a single word during this lecture, stop me, ask about that, okay? Because this is the most important topic probably of RL, of the entire course, okay? So please stop me and ask me as many times as you want, but make sure that it is clear to you. So MDP is basically a tuple of, again, I'll reiterate this several times just so that it is absolutely clear to you all, okay? It's a tuple of 5 elements: state, action, rewards, probability, and there is something called a discount factor, okay? Now what is, okay, you already know what state is. You already know what action is. We talked about it a lot. And you know what the reward function is, right? We did discuss about that, right? Now coming to the other element is P. P is the transition probability. So what is this transition probability? We talked about agent environment interaction, right? We talked earlier that how the agent takes random actions in the environment and it changes its states. That is, it moves from, say, this position to this position, right? Or any such action happens. So how does this happen? How do we know? Now, say somebody pushes me from behind. Okay, I'm standing here, somebody pushes me from behind. I move forward. Why do I move forward? Why do I not move back? Sorry?
He takes the next action because he knows state from his state is a function of history.
Okay, no, assume that there's no history, okay? I'm just standing here and somebody comes very randomly, pushes me, I move forward. Why do I move forward? Why do I not move backward? Or why?
Because the action is specific direction.
Okay, action is in specific direction. Okay, that is one way of looking at it. The other thing is, because the dynamics of a human or of any object is such that when it gets a push from back, it will move forward. You get that? So it is because of the understanding of that dynamics, you can tell that if somebody pushes me from back, I will move forward. With certainty, right? There might be certain action environment interactions where agent environment interactions where you cannot say with certainty as to what will happen when a certain action is done by the agent, right? Now say you you have a UAV. Okay, again we'll go back to the UAV example. You have a remote control, okay, and you thrust it up, right? It moves up. You know it will move up, okay. But say if the remote is not calibrated fully, and you give full thrust, what will happen? How far up will it go? Do you know exactly? Can you tell where it will go if it was not calibrated properly? You will not be able to do it. But you can say with some certainty or some degree of certainty that yes, it will go up, but you don't know how much. Right? So there is some kind of uncertainty. Okay? So these are the two kinds of transition probabilities that you have. Certain, which are called as deterministic transition probabilities, and then you have not so certain, that is uncertain transition probabilities, which are also called as stochastic transition probabilities. Okay? So in deterministic transition probabilities, you know for certain that a given action in a given environment by the agent will result in this state. That is, if it is in state S, you give it action A, it will go to state S dash. Okay? Now S and S dash can be anything here, but then you get the idea, right? With certainty, you can say 100% of the time this action will result in this state, if you are in this state, okay? However, there might be another scenario when if you take action A in state S, you might 80% of the time end up in state 1 or 20% of the time end in state 2. Right? You're not sure what will happen. Right? Assume a simple ball, okay? You're throwing a ball, okay? You know it will bounce and it will move forward. But can you, if the surface is uncertain, can you exactly predict the height, whether it will be 1 meter or 1.5 meter? No, you cannot, right? You will have some kind of knowledge about where it will go, but not exactly where it will go, right? This are called stochastic probability distributions, and this is deterministic probabilities, transition probabilities. Okay? Clear? Yes.
If the probability in the second state, you can stay in this place. يعني the probability divided to S1 S2, and the agent will take probability if they stay in the place, and move to S1 and S2.
You mean if it is in state S and there's an action A on it, there is some probability that it will not move to any of the states? Yes, that could be a probability as well. Yes, obviously. It might not. This is an example that I gave you here. But say probably it could be something like this. Like say 60% of the time here, 20% here, and 20% it will not move at all. That could be the case, obviously, right? Because the whole point here is it is stochastic. There is some, you have some idea of the probabilities of the transitions, but you're not for sure certain as to where it will go exactly. Yes.
If I know the initial, the agent, and the final destination of the agent, the main acceleration between them, does it will be fit in heuristic or?
No, can you?
I know the initial condition of the agent.
Okay.
And the final destination.
Okay.
Condition, and the main, if it's dynamic, I know the main acceleration of the agent. Does it fit in the heuristic or?
It depends. Okay, now say you have a car. You have a car, okay? It's moving with a constant velocity of say 110 km per hour. Okay? So after 1 hour, this car should exactly be 110 kilometers away, right, from its initial destination. Right? But by some reason I mean because of some deceleration here or here, it might reach only 108 kilometers. It will not reach the full 110 kilometers, right? So there is 90% chance that it will end up at 110 kilometers, but then apart from that as well, there is some probability that it might not, right? That could be because of simple noise, right? As in dynamics, there's something called noise, which relates to the uncertainty of the states, right? So because of that, you might end up at a slightly different position. Or maybe you accelerate a little bit more and you end up at 112 kilometers or 114 kilometers, for example. Got it? Was that the question? Okay, so yes.
So if it is like there is no stochasticity, so it's absolutely deterministic, like you suggest. The name is deterministic.
Yes.
But why probability? Like is the probability here 1?
Yes, the probability there is because of the terminology itself. There's supposed to be a generic terminology. Hence, the word P relates to transition probability divided into deterministic, stochastic. And when it's deterministic, it's 1. So yes. Okay. So state, action, reward, and probability, transition probability clear, right? Now coming to the last element, which is the discount factor. Okay. Okay. Also, said actions can be discrete or continuous, like I stated. Like states. Okay. States can also be continuous or deterministic. Okay. Now, transition probabilities, it can be what? You can have transition matrices, right? Or rather probability distributions, or you could have you can have directly discrete numbers. This results in this transition, this results in this transition, right? Or it could be vectors. Okay. Reward function is scalar. By definition, it is scalar always. Okay. So a reward function is basically just at every time step how good or bad that action is. You quantify it based on mathematical equations, so you will get a number. Okay. Yes.
Could you give us examples of continuous versus discrete states and actions?
Okay. So yes. Okay. So states, continuous states could be something like, say, when I'm moving forward as a human, cannot, or rather, okay, I'm moving with my joints, so I can be at any point here on the time, right? Like say this is a block, this is a world rather, okay? I can move, I can keep my step here. So between any 2 points, there are infinite points where I could keep my step of feet. So that is basically a continuous state space. However, if I assume that no, I can step only on the block centers, then it's a discrete one. So I can only step at one block at a time. I cannot be between 2 blocks. Okay? Similarly, actions, I can either move only right, left, straight or back, or I could have a continuous spectrum of actions. That is, I can move diagonally, I can move at any angle at any speed. Right? So this is the 2 classifications, discrete and continuous, states and actions. Okay. So yes, reward functions, reward is scalar quantity by definition. Right? So it will just give you a numeric value at that time step about how good or bad that value is, or that state is, or state action pair, as you will see later. Okay. Now discount factor. Discount factor is a very interesting element. Okay. So I use this example. Okay. You know something called time value of money, right? Okay. You must have heard a lot. Like there's some person, okay, who had say 1 million riyals in 1990, okay, and some person who has 1 million riyals today in 2025. Who do you think was richer?
The first one,
Why?
because of the inflation.
Because of inflation. That is the time value of money, right? The same value of money will reduce its value, or the value of that money will go down as time goes, right? So what does that mean? Like having 1 million today is better than having 1 million after 25 years, right? Similarly, in the rewards, okay, so what this reward function, what this discount factor does is, it will discount the effect of the rewards as time passes. Okay? Now let me give you an example. Say I'm moving from this door to that bottle again, that water bottle, okay? And I'm using some energy to go from here to there. Clear? I know that my energy will not deteriorate from this position to that position. Okay? Assume it will remain constant. Okay? Assume I'm a robot, or I'm a robot or something which has a battery, and the battery does not drain from start to end. Okay? So what will I do? I will simply have the highest speed, and I will directly go in a straight line and go to that water bottle. Right? So there, in that case, what happens is every time step will have an equal value, right? However, there might be some scenarios or cases where you want to get the maximum reward at the current step, and as you go forward, the reward might not be as valuable as getting it now, right? That could be one scenario. The other scenario is, how is this agent learning? Like I told earlier, it will simply interact with the environment by taking random actions, right? And you will see later in the algorithms that there are certain kind of algorithms which simply makes estimates of the future expected returns, right? It hasn't done that action yet, but it will just assume that taking this action will give me the best reward. Assume you're playing football, okay? You're a team of 11 players, right? You have the ball, you're moving forward. You see your teammate there on the right end of the field, okay? All you can predict is if you pass the ball to that person might, realistically and correctly probably predict is that you pass the ball to that person passes the ball to the next person. But you cannot make a map of all the possible passes that might happen from the start till it reaches the goal. Can you do it? I'm sure Ronaldo, Messi too cannot do it, right? Or whoever your favorite football player is. Even they cannot predict it, right? So that means that you can only take actions with up to a certain horizon with certainty. Beyond that, you don't know, right? You just assume and expect it to be the series of actions that you wish it is to be, that series of actions, right? You pass the ball to that person, you expect that person to pass it in such a way that it reaches the other person with this certainty, and then to the other person, and then to the other person, into the goal probably, right? But then you see this, the level of uncertainty keeps on decreasing as the number of steps move forward. You get the point, right? As the number of steps increases, the uncertainty of your decision you're taking now increases. Therefore, the reward that you expect you will get in that step, in a far off step, might not be the reward that it is, right? It will be slightly lesser probably, right? So for that, you have something called discount factor to account for that uncertainty. Clear?
So the discount factor is added to the reward,
Multiplied with the reward.
multiplied with the reward.
So
it will be either 0 or 1, or it can be 0.5, 0.7.
it is a continuous value between 0 and 1. It can be anything between 0 and 1. 0 meaning it's very short-sighted. You don't care about what's happening next. You want all the rewards now. 1 implying you want to have, you assume that you estimate the rewards right till the end of the episode, right? If it is 0, you basically, all you care about is, there's a person here, I'll pass the ball to him. You don't care whether he can pass it to the next person or not. You just assume, you just see, okay, this is the best possible pass for me now, irrespective of what the team goal will be, right? If you have a discount factor of 1, it means you calculate everything till the ball reaches the goal.
So from each step, suppose in one case, discount factor is added to 0.5, suppose.
Mhm.
And another future case, so that value will be increased to 0.7 like that, and 0.8 because the value should be higher than the previous value.
Higher, how do you mean
Suppose
higher?
we are getting 10 reward
Okay.
and past case, another case you want to make it 10.2 or 10.3. So when I multiply the value with the school is not getting multiplied. And future case we will multiply 0.3 or 0.7. How we will make this range to the value between
Okay.
0 and 1.
Okay. Thank you for bringing that up. Let me explain the concept here before I move on. Then, in that case, now this is a grid word, okay? Basically a discrete word. This set of actions you can take are discrete here. You can either move forward, right, left, or back. You cannot move diagonally between blocks, okay? So you have a very limited action space here. This is your action space, and every block here is a state, okay? Let's even name it. Okay. So 3D is your start, okay? 1A is your goal, 3C is a fire, or simply you don't go there, okay? 3C is basically a pit, you'll fall there if you go there. Okay? Now you, as an RL agent, have to come up with a series of action or a series of set of actions that will take you from the start position to the goal position in the least possible steps. Okay? So what are you doing? You don't know anything. All you know is that if you give it an action, it will simply take that action. Say you are now in 3C. Okay? And this series of action that you will formulate will form something called a policy. Okay? Policy is basically the set of actions that you have, the series of set of actions that you have in order to solve the problem optimally. Okay? Is it clear? 100%? Any questions, anyone up until this point? Yes.
For it to be a policy, does the solution need to be like optimized? That's the
Yes.
condition.
Yes. In fact, the way our algorithm solves, the output that the policy you get is optimal by definition. So there are mathematical proofs for that we'll see. So the policy that you will get upon convergence will be optimal.
And what kind of optimality? Are we talking here exact or global or near?
No, it is global. It is global optimality because we'll be using something called Bellman equations to solve the value function and the state value functions to solve. And the solution that we'll be getting is, well, yes, it is assumed to be globally optimal. So yes, it will be global. Okay. You're here. Okay. Every step you take, okay, because you are dispensing energy, you get -1. Okay. If you fall in the fire pit, you get -5. If you reach the goal, you get +10. Okay? Clear? Now, first this agent takes an action, go forward. What will happen? -5. And, okay, and there are something called episodes, okay? Like in games, I'm sure you might have played games where you lose a life, you restart, right? You restart from a given checkpoint, right? In games there are checkpoints, right? So you simply respawn in a given checkpoint, okay? So now you fall here. What happens? That episode is over. New episode. So this is episode 1. This is episode 1. Make it take it up. 2, 3, 4, 5, 6, and so on. Okay. So first episode, the total reward is how much? -1. Okay. Now, next episode, the agent starts. The agent now somewhat learned that do not go forward. 3C is not a good state. It will learn that 3C is not a good state. Okay. It can learn two things. Either there are different kinds of learning that will happen here. Okay. Either it will directly learn that 3C itself is not a good state, or it will learn that if you are in 3D and you move forward, those combinations are not good, right? So you have what? So either 3C is bad, or moving forward in 3D is bad. Okay? Now, this is simply a state. This is basically a value function. This is something called a state action pair value function. Okay? So we will talk about that later. But now, okay. So first episode, it learned do not move forward. Next episode, what it does is it will go down. Go down. So what's the reward it got now? -1. Because it lost energy, right? It again moves forward. But it cannot. That's an invalid action. So it's supposed to take another action. Okay? It does not end the episode. Let's assume it does not end the episode. It simply does not do anything. Okay? So now it takes a right turn. What happens? Again, nothing. So it simply tells the agent, no, take another action. This is an invalid action. So it will move to the right. Okay, yes. And now the agent is here. Okay. What's the reward it got for this action?
-1.
-1. Okay. Now again, it will be 2. Okay, let's do it again. It moves up. What will happen? -5 and terminate. So now the total episodic reward is what? -1 plus -1 plus -5. -7. Okay? Yes.
I guess -1,
Uh-huh.
and the reward for farming. What else?
Yes, that could be one way of calculation, but no, I'm simplifying the problem here actually. Yes, but in real scenarios, yeah, you might have that step penalty plus that penalty itself of whatever you're doing. But yeah, let's make the calculation simpler here, okay? So -7, you fall here in the pit. Restart, again it comes here. -1 again, -1 again, this time it doesn't go up. It simply moves forward, okay? So -1, again forward here, -1, up, -1, up, -1, up, -1, come here, action -1, but then it reached the goal, so the reward it will get is +10, okay? 1, 2, 3, 4, 5, 6, 7, plus, so you get +3, right? Is +3 the best reward value return it can get? Why? There's a smaller part, right? So assume it does again that for many episodes, okay? Finally, the agent realizes that okay, I simply go up, go left, go left, go left. So 1, 2, 3, 4, 5. -5 plus 10. Total value +5. So which is the largest number here? +5. Right? So the highest reward it is getting is +5. And the action policy is simply up, left, and left, right? Left, and left. Okay? Now this is in a scenario where I know exactly that this agent will do exactly with that, will take that action or will end up in that state if I take that action, right? Assume now a scenario where there is a wind blowing here, a cross wind blowing here, okay? And even if you take this action, it might simply end up in a different position, right? There you're uncertain now, and you're uncertain whether the wind will constantly blow or not, okay? But you just know that it might blow, right? So what are you doing now? Can you be for sure certain that this series of action will exactly lead you to the optimal path? No, right? Now you're uncertain about your calculations. So what you do is you discount your uncertainty from the expected reward. Okay? Assume that now at the discount factor, let's assume that gamma, the discount factor is 0.9. Okay? Simply less than 1. You're still very confident, 90% sure that yes, this is good calculations and good estimations, but you're not 100% certain, okay? So you're taking a discount factor of 0.9, okay? So what you are doing now, this step, first step, okay? It will, basically this is how you calculate, okay? Gamma power n times r is your, yes?
So the result would be the multiplication of K1 with the
Discount factor, power the number of steps you take. Okay, basically that's multiplication. That's why you get times n, okay, or rather power n. Okay. So what you're doing here now is for step 0, okay, you're 100% sure that this step will result in this action. So I can be sure that I will get this reward. So you simply take -1 times discount factor of 0.9 times 0, which is -1, right? So your return for the first step is -1. Next step, okay, now here you remember you had -1 plus 10. That's why you got +5, okay? So up until this point it is same. First step -1, okay? This is the optimal policy we have based on discount factor of 1, okay? Now the next step, okay? Now here you're multiplying it -1 again, but this time 0.9 times 1. So that would be -0.9. Okay? So now you are slightly giving it more advantage. You're like, okay, maybe it will get a slightly higher reward. It will get -0.9 instead of -1. Right? Next step, it will be -0.81. Right? Because it is now -1 times 0.9 squared. Right? And so on and so on and so on. Can somebody please do the calculations for me? 0.9 power 4 is how much? What I have a calculator.
0.6561.
Okay. 0.6561, and you have finally 0.59. Okay. So you see now your values are slightly improving, right? Or if it was positive, it would slightly go down. So what does this mean? This is something where you're accounting for the uncertainty in the future that you might have. Okay? Okay? So you're basically telling that the reward that you're getting now is better than the reward that you are getting later on. Not in terms of numeric value, but in terms of certainty. You're like, yes, now I'm more certain, this will be my value. As you move forward, you're like, I'm uncertain, so let me reduce its value a little bit. Okay? Now the reward value that you will get would be somewhere around plus 6 point something. Okay? So you see, now you account for something called discount factor, or you account for uncertainty with something called discount factor, the value of which can range from 0 to 1. Okay? You see? So therefore it's the model's preference for immediate versus future rewards. Yes.
And in the discount factor, you are taking a power.
Yes.
How you would take the
For every step, the power increases. Because it is cumulative, it is compounding here. You will see. This step it's 0.9, right? This step it's again 0.9 times 0.9. This step again it's 0.9 times 0.9 times 0.9, right? Because it's cumulative. So you multiply it, right? Okay. Yes.
Can you another situation if every action is scored in this board is negative one, and the small number by negative is a short has to move with the row.
Okay.
Salim one. This is the rest. Salim one.
Okay.
This the small number is the best. If we take another best, the number will be big. Then this.
Yeah, that's what is happening here in the reward calculation. You will see when it took this path, the total return it got was plus 3. Whereas when it took the shortest path, the return it's getting is plus 5, which is a bigger reward or bigger return. That's why it will prioritize getting the highest reward, highest possible reward. Is that the question? Yes. Yes.
So between 0 and 1.
Mhm.
Again, to make sure I'm understanding. 0 or 0.1 or a small discount factor, it means that I'm not certain about the future reward.
Short-sighted, yes. You want immediate rewards.
Okay. A large discount factor means I want more future rewards.
You're giving more equal importance to the future reward as you're giving it to now. Right? So it's far-sighted basically. Otherwise, if you have 0, it means you don't care about what happens after the first step. Yes.
Yeah, in this case, we will probably have two optimal paths. You said that the discount factor will refer to the immediate answer, the immediate optimal path of the
Right.
mind. What's going to work? I didn't understand. And the discount factor, we have two optimal paths actually.
Yes, we will have multiple optimal paths. But the thing is, the optimal path is what? Where you have the highest expected return. So for every optimal path, you will have the equal value of returns, which will all be same, which should all be same value.
Let's suppose we have two similar paths.
Okay. Okay.
How is going to have discount factor?
Then you will get the same reward because see, if it is the same path, then you will, in this simple case, it would mean that you are taking same number of steps, implying that the discount factor will compound same number of times. You get it?
Yeah.
So therefore, irrespective of the path, the direction of the path, you will take same number of steps, implying you will accumulate same returns.
Same point.
Got it?
Yeah.
How to calculate the value of the discount factor based on the uncertainty or the level of the uncertainty?
See, it's not just uncertainty. So what here you can do is, say for a control problem, okay, you have a goal that you want to reach. You simply take 1, because your objective is to reach that goal or complete that task, right? So it doesn't matter if you do one step correctly and rest all wrong. So in that case, what you're trying to do is all the steps, right? All the steps should be equally important, because then you will reach the goal. Okay? But in certain scenarios or certain cases or applications, you will see that you do not care about the future as much as you're caring about this very step. And the value of that, the reward value keeps going down. You see my point? Yes.
So would the same logic be for having a positive reward balance? So instead of -1, you have
Plus one.
+1 for
Okay.
every time.
Okay.
So would it be the same logic where at the end you have a higher reward than if there was no discount factor?
Yes. Okay, now why will that happen? I'll tell you. Say you're telling me you get +1 for every step here, right, and not -1. So your cumulative expected return will be with. Okay, in that case, what you're doing is you are. Sorry.
Minimize it.
Yes, but then you're giving a reward at every time step, which is not the case often. Okay, you design a reward function such that it means so the agent will not even move forward in that case. You know what it will do? It will simply keep oscillating between these two steps, because it will have the reward system. It's getting a +1. It's like, okay, I come back again +1, move forward +1, +1, +1, +1, so it will get infinite rewards. That is something called reward engineering. So how you design your reward function will determine whether your RL agent will actually solve the problem or not. Or it will simply hack it in a way that it will keep accumulating rewards without solving the task, right? That's why you have to formulate a reward function such that it does not hack this, it does not do this kind of things, right? Otherwise it will simply keep oscillating between first and second step. First step it will get 1, come back again +1, for 1, 1, 1, 1. So what is the incentive of it for moving forward? It will not, right?
I think you can say also the opposite for weight back and forth if it's negative. So the agent might not want to move because you will keep getting a penalty.
No, but then when it is moving forward, it will see that for some steps it is getting large negative, for some steps it's not getting as large negative. And when it moves forward, it sees that it is getting a huge positive somewhere at the end, right? Even with positive, that might happen. But then usually in RL, for control settings at least, you don't have a +1 for every step. You get it? Yes.
Doctor, will adding the uncertainty factor change the optimal path?
No.
So what's the point of it? If we want to know the optimal path, so we can find it without dealing with the uncertainty, right?
Yes, but then assume this scenario, okay, where you don't exactly know where it will end, where there is some kind of stochasticity in your agent's action. Then this kind of reward function will balance it. But for most practical applications, the discount factor value that you will be taking is 0.99 basically. So with almost 1, right? For control applications, it is mostly 0.99 or 1 even for some cases, right? Yes.
But in optimization, like when I'm using RL to optimize, to begin with, like remind me, Gottman's equation is the discount factor to the power of n?
Yes. Yes.
Yeah?
Yes, I'll check the equations again. I have it now, but it is summed to n.
It is multiplied. Like it is multiplied by first future word plus second future word.
Yes.
If I remember correctly, it's not to the power of n. I might be mistaken.
Let me check. Yes, I will just check in just a minute. Yes, here you will see for the value function, it is gamma power t times r, implying that it is multiplied by the number of time steps here, or rather it is powered to the number of time steps here. Gamma power t. So for every time step t increases, gamma value multiplies that way.
So what is the Q and where you're multiplying gamma times the max?
Yes.
What is Q star of SNA?
Okay, I'll explain this another time. I wanted to come this later, but okay. this is basically a state action pair. Okay? What you can, like I said here, you have two ways of determining the reward for that particular step. Right? You either assume that no, this state itself is bad, or you understand it in a way that moving forward in this state is bad. Right? So the first one, Vs is basically the value of that state. There's only one function here. V is a function of only the state. Okay? Whereas Q is a pair. It takes into account both the state and the action. So then it tells you that taking this action and this state is bad.
Is Q like the cumulative reward from Q learning?
Q learning comes from Q star. So yes, when I come to that probably it will be more clear. But then yes, that is how it is. So it is multiplied, it is to the power of the number of time steps that we have.
So my question was, like, so in the realm of optimization, so we use the discount factor to intensify and diversify and intensify the search, because like
Yes.
like or the way that we account for the future possible reward, right? So like how like speaking of that, in context of global optimization.
Okay.
So if I like for hill climbing, then I would like typically then Q would be that high, would be 0.99.
Q
Not Q, I mean gamma, the discount factor.
yes.
Would still be that high?
Honestly, it depends on the kind of problem you have set up first to begin with. Right? I think if we reach that
Sure,
point,
sure.
then it will be better for me to explain
By all
it.
means, I didn't mean to have you jump that.
Yes, yes. So I'll get back to that. But okay, yes, I'll get back to that point. Yes.
In first stage we are taking minus. That means you are considering discount factor power 0.
Yes.
That means it is number of steps minus 1.
That is step 0 basically. Then step 1, then step 2. You have to take some steps. So that is step 0. Yes. But that would be immaterial, honestly, because consider it step 1 or step 0, it will uniformly change that for every episode. So as far as it changes for every episode uniformly, it's fine. You take it as 1 or 0. But for the sake of calculations here, and that's how it is done actually. So that is considered step 0. Okay. So we talked about the elements, right? State, action, and transition probabilities. It can be discrete, continuous, or vector valued. Action, it will be discrete or continuous again. Transition probabilities can be deterministic or stochastic, right? Clear up until this point?
Yes.
100%.
Yes.
Anything? Sure. Okay. Reward function again, like I said, it's a scalar quantity, right? Which will tell you how good or bad that particular instant is. Either that particular combination of state and action or that particular state. Yes.
Sorry, regarding the last slide, you said when in the last part of the probability, the deterministic and stochastic case, at least in the realm we're talking about, does this affect how we choose maybe gamma, other parameters? Or?
Yes. Yes, absolutely. Absolutely. You will see. We will be doing an example probably next class. So in that class, you will see like how that will affect, how gamma will affect, how different parameters will affect your overall calculations based on the stochasticity of the environment itself, or the transition probabilities. Okay. So it is a scalar value quantity. Most important thing, it does not. The total rewards that you get, or the sum rewards that you get for the entire episode from the start to the goal is called what? cumulative reward. What are cumulative rewards? It is the return basically, okay, which is called the episodic return. For that episode, when you run, what is the return that you're getting? Total return, sum of the rewards at every time step. Okay, reward and returns are different entities. Okay, yes.
Reward can be immediate and intermediate. Why? Every time send immediate only, I can get the reward intermediate. Say if I make chess, I can lose one piece or to win futures again. Immediate. If you take action, reward or penalty.
Yes.
Intermediate, you can get reward after time.
Okay. Yes.
Yes. I think here evaluate the intermediate speak of taking action.
Where is intermediate, by the way? Immediate.
Yes.
Okay.
Only or not?
Yeah, reward is immediate because you need to know every action or every state it is good or not. Either zero, negative, positive, whatever, but you need to know immediately. Right? Otherwise, say if I'm going to that bottle, okay, and you tell me that I will get a reward only after taking 10 steps, okay, and I simply decide to walk here. In 10 steps, I reach the dead end of the road. Then you tell me it's bad. So I don't know whether the first step I took is bad, or the second, or the third, or the fourth, or the 10th step. Right? So I need to know it every step in time whether that step is good or not. Right?
But sometimes it's not good. If I learn how to walk, if I get him 0 or 1 in every step he take, he didn't learn. If I get him reward intermediate by the time, he can learn good.
Yeah, that is what your cumulative reward will do. That is what your return will do for the episode. But every step you need to know whether it's good or not. Right? Okay. Okay. For example, say you're riding a cycle. Okay? You're riding it for the first time. You don't know how to ride a cycle. Okay? You sit on a cycle. Okay? And you decide to press the pedal which is already done. Will the cycle move forward? And will the instructor, whoever is teaching you, will he let you be like, okay, no, keep doing that, keep pushing back. You press the pedal that is already done 10 times and then he tells you, no, what you did is wrong. So how do you know which was wrong? The first step you took, the second, the third, the fourth, or the 10th? You need to know at every step whether this action is good or not. You get my point? So rewards are immediate for every time step. Returns is for the cumulative. Okay? Okay? Return, reward. Okay?
So
Yes.
does the agent first calculate the reward, then take a step, or first take the step, then calculate?
No, right. Okay. Now I'm moving forward. Okay. Give me a reward. I took an action. Give me a reward. I didn't take any action, so you cannot give me a reward. Now, am I moving towards the water? Yes. So now you will give me the reward. Right? You get the reward after you do the action. Right? You get your report cards, for example, after writing the exam.
If I know the states, for example, then I can calculate the reward in advance.
Oh yeah, absolutely. In fact, that is one of the paradigms that we'll be studying. It's called dynamic programming. We will come to it. But here the entire point is you don't know the states. So what you're doing is you're doing trial and error. You don't know the states, where you will go, how you will go, or rather you will know how you will go to the transition probabilities, but you don't know how that state is. So you basically do trial and error. Right? But yes, that is how we'll be calculating in one of the paradigms. You already know the estimates and you calculate it. Okay. So, okay. Another important thing about reward function is, like your colleague mentioned here, is that reward functions should be designed in a way to explain or to let the agent understand what it needs to do, not how it needs to do. Okay? This is a very, very important distinction that you need to understand. What? How? A good reward function will ensure that it teaches the agent what to do, not how to do. Okay? We'll spend some time understanding this. Okay? What to do, how to do. You understand the difference? Now, again, I'm moving forward. Okay? No, rather, my goal is to pick that bottle. Okay? Now, will you tell me that I need to lift my leg with this velocity at this angle and then keep it, then do the same thing with the next leg? Or will you say, because I already know that I have to move my leg this way, or I learn, okay, even if I don't know, say I'm walking this way, but I realize that this is a bad way, because of the friction, say you design the reward function such that it gives me penalty if I rub my feet to the ground, and rather you would give me, say, positive penalty if I lift it up and I move forward, right? So now, if you simply tell me that I need to pick that bottle up, no matter how I do it, okay, but you design the reward function such that the series of action are the optimal action and the way you want to do it. Okay, there are pretty funny videos that you might come across. I'll show you in fact in next class, where not good designed reward function will result in the objective being achieved, but in a very funny way. Right? Like say suppose there's a dog, okay, and you tell it to go fetch a ball. Okay, there are many examples, okay, of training simulations where the dog doesn't learn how to move its legs. Okay, it simply hops on one leg and it goes to the ball and collects it, because the reward is designed that way. Right? So reward engineering is a very important aspect of reinforcement learning. You need to design a reward function such that it incentivizes the agent to learn what to do. Okay, but yes.
It's just like the distinction, the differences between what and how are not as clear. Like how different is what? The question of what and how different these two questions are.
Okay, I should probably try to explain it with an example. Okay? Assume you have a swarm of UAVs. Okay? They're all moving in some direction to do some task. Okay, that's irrelevant here, immaterial. You incentivize the swarm, okay, to catch this good, to catch this, say, dog or ball or whatever it is. Okay, the drone should simply go, the swarm of drones should go and capture that agent, whatever it is here, okay, that entity. Now, if you, that is what should be done, right? Now, coming to how it is done. Now, assume you design a reward function such that you give values to how close these are, okay, and whether or not it is how this entire swarm is actually circling it or not, who detects it first. If you keep rewarding it for everything like that, then it is basically explaining it how to do exactly. Let me make it more clear. Now, if you okay, now say these two drones. Okay, you have these two drones. You're moving forward. Okay, the way you encircle it. Okay, you have to encircle. That is the whole goal. You have to encircle, say this dustbin with a swarm of drones. Okay. Now, if you instead of simply telling the agent that simply telling the swarm of the agent that you must follow a certain path or a certain trajectory around that object, right? Say a circle of radius this thing, right? This agent should be able to do it without having to know the interdistance. If you are explicitly hard coding the interdistance term in the reward function as well, then it's not learning basically. It's just trying to, what do you say? Imitate what? No, it is trying to simply.
What you
Yes, it is not very generalizable. You get it?
I think like what you mean is that like if I may, like you mean like we don't wanna dictate like how and be worried about the question of how. I'm worried about the objective rather, right?
Yes. But at the same time, when we are designing the reward function, it shouldn't be a very hackable reward function. In the sense the agent should hackable.
What does hackable mean?
In the sense that, like our colleague said, that say if we keep giving it +1, okay, what in that case the agent will simply learn to exploit that reward. It will take one step +1, it will go back +1, and it will keep doing that forever. and it will accumulate infinite rewards, for example, because if say the episode doesn't terminate, it gets infinite reward. We don't want that to happen. We want to design the reward function in such a way that the agent is not able to exploit the reward function that we have in a way that it will get the objective in a way that we want without we telling it in the way that we do. Right? Yes.
Yeah, I just wanted to add to your discussion is that let's say that the reward function is positive, so the agent would go up and down to increase its reward. Yeah.
Right.
One way to stop this hackability is that we can add like a time. The longer that time it takes the agent, then the reward will
It goes.
Yeah.
Yes. Yes.
We
So
need
that's
to
why.
find a way to manage the reward function so that it doesn't.
Yes, that's why we had this example of -1, assuming that the time series was also discrete. That every time step is 1 unit. That's why you take one step, you get -1. Second step, -2, such and so forth. Yes.
Regarding this problem, we said like we don't want to give the distance between the drones and not give every detail. But usually we give constraints. Like for example, like keep a safe distance from the drone. Or when you form a circle in a certain trajectory.
Yes,
So
constraint
what's
is
the
a different thing. Constraint is a different thing. Say, this is honestly a raw example I gave that came to the top of my mind. Might not be the best example, but then constraints are different from explicitly encoding the details that you want of how it should work.
Okay, so do the task whatever you want.
Exactly.
Keep the constraints that I put to you.
Exactly. Do the task what you're supposed to do with respecting the constraints. I won't tell you how to do it,
Okay.
but you have to find the best way. If you, after training, if you see that it is not the best way, you re-engineer your reward function. You're like, oh, probably because of this term. That's why you need to understand your reward function very clearly and fully. Right? Right?
Yes.
Okay. So, see, an example of a reward function here is, say the UAV is supposed to go to a desired altitude, okay, 5 meters or something, right? You don't tell the RPMs, you don't design the reward function in such a way that, okay, fine, if you're not at this RPM, you will get a penalty. No, you don't do it. You simply say, if the error of the distance is something, then you get penalized for that distance. So it will simply try to reduce that error distance, right? Because you see here, as your x and x desired gets closer and closer, the error, the penalty you're getting, the negative term here keeps getting smaller, right? At 0, at x desired and is equal to x, you simply have a 0 penalty. You don't have any penalty. That's the ideal situation, right? The other term is basically a square. In this, you are trying to control the action in the sense that the actions don't go up and down very quickly, like bang control, right? There's something called bang control where you only have 2 modes of inputs, either 0 or 1, 0 or 1, 0 or 1. Okay? You don't want that to happen with your physical motors, right? You'll burn your motors, right? Clear?
So this is an indicator of how fast the motor is, or the action is changing?
Yes. Right? You could even take AT minus AT minus 1. In this AT minus AT minus 1 equals here. So this will penalize the change of actions. That means there is no rapid change of actions. Here it will simply ensure that the thrusts are not very high. For example, if action is a thrust, thrusts are not very high. Because say a higher value here, square, will give you a very high negative reward. Right? Which is a penalty basically. Okay?
Instead of putting a thrust limit change, for example.
Yes. Yes. Instead of a thrust limit change. Yes. Okay? Clear until this point? Yes.
What's x? What's x?
The position. The position. It can be a vector, it can be simply x in one direction, it can be anything.
How does that include the terminal reward in this case?
Sorry?
Like it says here, include terminal reward for success and failure.
You could. In this example, it does not. But then you could have it. Say plus 10 if x desired minus x. You could have conditional reward functions. Reward functions need not be continuous, right? So you can simply have, apart from that reward, a last term, something like this. If x desired minus x less than 0.1, okay, then multiply this by say 5. plus 1. So it means when your distance error is less than 0.1 or whatever threshold you define, then this value will simply become 1, right? And you multiply it by 5, so you get plus 5. You could have that as your terminal reward function, terminal reward. But you need not in this case because it simply tries to reduce the error, and here the best case scenario would getting a reward of 0 rather than any positive value. The reward curve itself would be like this. It starts with something negative, say negative 1000. The maximum value it can get is 0, right? Okay?
So in hope here of, like in this case where I have no positive reward, so in hope of minimizing, I would end up with a negative reward,
Yes,
right?
yes. Your best case scenario will also be negative, very close to 0. Right? And that's fine. The agent will try to reach as close to 0 as possible.
Yeah, which would mean less steps, right?
Not necessarily, but it just has to do with the way the optimization happens. So if you have positives, then it will not be a very stable learning curve. Say you have intermediary steps, okay? Like say suppose when for path following robot, okay? Say when it reaches 5 meter, give it plus 5. And when it reaches 10 meter goal, give it plus 100. Right? Then your learning might not be very stable, or it will be in such a way that the agent will simply go there, stay in that state forever. Because it's getting plus 5 for every time step it stays in that step, right? So that's why it's usually avoided to give a positive value in between the tasks. It's usually for the terminal stage. Or you simply don't even have that. That's fine, it will still learn. If it does not, that's what reward engineering is all about. Like if you think that this reward function is not letting the agent learn correctly, or you feel that the agent is not learning correctly and you want to improve the learning, you change the code. You add a plus something or this kind of term there at the end, that's fine. Right? Transition probabilities, we already did talk about it, right? I want to start Markov property next class, so I'll talk about this because we have just what 9 minutes. Okay. So yes, again, transition probabilities, you have stochastic, you have deterministic, right? Yes, here you have a definite model or a definite equation where we'll see this state, this action, some function of that state and action will give you a new state, right? Whereas say there is this wind disturbance, where wind disturbance itself is a probability. Okay? Say this is a normal probability distribution with 0 mean and mu square as the standard deviation, sorry, sigma square. Then you have xt plus vt delta t, right? What does this mean? That the next position will be a current position plus the delta of the velocity times time plus whatever the wind disturbance effect is. Here, now this will give you a stochastic state. You're not 100% sure, right? Because there is some kind of probability distribution involved. Right? Clear on it? 100%? Okay. So next class we'll be talking about Markov properties. Okay? Why Markov property, what Markov property is, and how it relates to output. Okay? Up until this point, any questions?